This video is primarily about the graphical nature of logarithmic functions. This is AP Pre-Calculus topic 2.11. If you appreciate this content, please give it a like. Here's the general form of a logarithmic function. B has to be greater than 0 and it cannot equal 1. A cannot equal 0. Otherwise, we would have nothing. I want you to memorize that the graph of a logarithmic function has this basic look to it. This is the parent function when the a value is positive. If the a value is negative, it's going to be reflected over the x-axis, and then it will look like this. Notice that a logarithmic function in this form will always pass through the point 1, 0. Notice that the y-axis is a vertical asymptote. So as x approaches 0 from the right, a logarithmic function will approach negative infinity or positive infinity if it's reflected. Because the logarithmic curve does not reach or pass the y-axis, the domain is from 0 to infinity, not including 0. It never reaches the y-axis. The range is negative infinity to positive infinity because the log function does go down and up forever. Notice that a logarithmic curve is either always increasing, like this one, or always decreasing, like this one. It never switches up in the middle. Also, a logarithmic curve is either always concave down, like this one, or always concave up, like this one. Because logarithmic functions approach the y-axis asymptotically, the left end behavior limit statement will always begin the limit as x approaches 0 from the right. Remember, approaching 0 from the right is always denoted with this little plus sign superscript. One more time, be careful. We will not say the limit as x approaches negative infinity for the left end behavior of a log function, because a log curve does not approach negative infinity. It stops at the y-axis. Example 1. Write limit statements for the end behavior for the following logarithmic functions. Part A. For the left end behavior, be sure to say the limit as x approaches 0 from the right of f of x. And we see that as x approaches 0 from the right, f of x approaches negative infinity. The right end behavior will begin the limit as x approaches positive infinity of f of x, as usual. And we see that as x approaches positive infinity, f of x also approaches positive infinity. So the limit equals positive infinity. Part B. For the left end behavior, we will say the limit as x approaches 0 from the right of h of x. And we see that as x approaches 0 from the right, h of x approaches positive infinity. So this limit equals positive infinity. For the right end behavior, we will begin the limit as x approaches positive infinity of h of x equals. On the right, h of x is falling, so this limit equals negative infinity. For part C, we need to sketch our own graph. The a value is positive, so this logarithmic curve will look like this. So we begin the left end behavior with the limit as x approaches 0 from the right of g of x. Make sure you are using the correct function name. And as x approaches 0 from the right, g of x is approaching negative infinity. So that's the limit. And then for the right end behavior, we will begin the limit as x approaches positive infinity of g of x equals. On the right hand side, g of x is rising. So this limit is positive infinity. Just for comparison, if I had k of x equals negative 2 log base 3 of x, that would be a reflection of this graph over the x-axis. So this is when the log graph is decreasing, and it looks like this. Example 2. For each of the following, determine if the logarithmic function is increasing or decreasing, and concave up or concave down. For part A, we are given the graph, so we can plainly see that this logarithmic curve is concave up. Concave up means being part of a bowl shape. So if I were to sort of continue this like this, you can see that we have the bowl shape, and the curve is like the left side of a bowl, which still counts as concave up. We can also see that from left to right, the curve is decreasing by the way it is falling from left to right. So concave up and decreasing. We can see that graph B is concave down. It is the left side of an umbrella shape, so that's concave down. And also, from left to right, this curve is increasing. It is rising from left to right. So concave down and increasing. For part C, we need to draw our own graph. When the A value is negative, the curve looks like this. And this will be concave up and decreasing, just like part A was. Example 3. Selected values of several logarithmic functions are shown in the tables below. For each table, find the value of the constant k. Notice that f of x has output values that are equally spaced. In a previous video, we learned that for logarithmic functions, when the output values are equally spaced, the input values will vary multiplicatively. In other words, the input values will have a common ratio. The first ratio is 2. 2 divided by 1 is 2. That means the next ratio must also be 2. So if we multiply 2 by 2, that will give us k is equal to 4. And then we can mentally check by carrying on. If we then multiply that by 2, 4 times 2 is 8, and the pattern continues. So k equals 4. For g of x, again, the output values are equally spaced. So the input values will vary multiplicatively. 18 divided by 6 is 3. So we know that the common ratio has to be 3. We can use division to work our way backwards through the input values to find the value of k. 18 divided by 3 is 6. 6 divided by 3 is 2. So k must equal 2. For h of x, we see that the output values are equally spaced. However, there is no common ratio found between the input values. The only way h of x is some kind of a logarithmic function is if this is the translation of a log function. We need to add or subtract from these input values until we find numbers that do have a common ratio. Let's start by adding 1 to all of the numbers. That gives 5, 6, 8, still no common ratio. Subtracting 1 gives 3, 4, 6, still no common ratio. Adding 2 gives 6, 7, 9, still no common ratio. Subtracting 2 gives 2, 3, 5, still no common ratio. Adding 3 gives 7, 8, 10, still no common ratio. Subtracting 3 gives 1, 2, 4. Wait a minute. 1 times 2 is 2. 2 times 2 is 4. So we are getting a common ratio. Subtracting 3 from these last two numbers gives us k minus 3, stuck with an expression there, but then 16. So continuing with the pattern, of multiplying by 2. 4 times 2 is going to give us 8. So that means this k minus 3 must equal 8. Let's drop down here. K minus 3 must equal 8. Therefore, k is equal to 11. We can sort of check this answer by following through. If we multiply by 2 again, 8 times 2 is 16. For L of x, we see that the output values are equally spaced. Let's see if the input values have a common ratio. To find the common ratio, we divide each term by the previous term. So we will find the first ratio by dividing e by e to the negative 2 power. Remember your properties of exponents. When you divide with like bases, you subtract the exponents. For example, b to the a power divided by b to the c power is b to the a minus c power. So e to the 1 power divided by e to the negative 2 power is equal to e to the 1 minus negative 2 power, which is e to the 1 plus 2 power, or e to the 3rd power. So that's the first ratio, e to the 3rd power. Skipping down to the other pair that we can see, e to the 10th power divided by e to the 7th power, subtracting the exponents, we get e to the 3rd power. So we do see a common ratio of e to the 3rd power. That means to get from e to k, we are going to again multiply by e to the 3rd power. E times e to the 3rd power is e to the 4th power. So that answers the question, k equals e to the 4th power. Let's double check by following through. If we multiply by e to the 3rd power again, e to the 4th power times e to the 3rd power is e to the 7th power. So this is definitely correct. Example 4, find the domain and range of the following logarithmic functions. The graph of the parent function y equals log base b of x looks like this, and all of these other logarithmic functions are going to be transformations of this. Notice that the range of the parent function is negative infinity to positive infinity. Vertical and horizontal translations will not change the fact that the range is negative infinity to positive infinity. Neither will vertical or horizontal dilations. So the range of any logarithmic function will always be negative infinity to positive infinity. Now we can focus on the domain. Here's a basic sketch of f of x for part A. Notice that a vertical dilation does not change the domain, which will still be from 0 to infinity, from the vertical asymptote to infinity. Be sure to use a parenthesis at the 0 because the 0 is not to be included in the domain. Y equals 0 is the asymptote. The curve never reaches that asymptote. It never reaches 0. Part B. The graph of g of x has 3 transformations: a reflection over the x-axis, a vertical dilation by a factor of 5, and a horizontal translation by 3. The vertical dilation does not change the way the basic graph looks from the parent function, so you can almost ignore that. But the negative a value does mean that the graph will be reflected over the x-axis, so it will look more like this instead of this. However, then the minus 3 means a horizontal translation by positive 3. So we need to shift this graph 3 units to the right, including the vertical asymptote. This horizontal translation by 3 is the only thing that's changing the domain, which will now be from 3 to infinity instead of from 0 to infinity. Again, use a parenthesis on the 3 because the vertical asymptote cannot be included in the domain. So 3 to infinity. Let's use a shortcut to find the domain for part C. Notice that all we needed to find the domain for part B was the vertical asymptote. We could have found this vertical asymptote by setting x minus 3 equal to 0 and solving. And then we get x equals positive 3. There's the vertical asymptote, which will give us the domain. For part C, we can find the vertical asymptote by setting 2x plus 3 equal to 0 and solving. So subtracting 3, we get 2x is equal to negative 3. Dividing by 2, we get x is equal to negative 3 over 2. So the domain will be from the vertical asymptote to infinity. Be careful, none of these examples had a reflection over the y-axis, which shows up as a negative sign on the inside like this. If there was a reflection over the y-axis, instead of the graph being to the right of the vertical asymptote, it would be to the left, like this. So in this case, the domain would go from negative infinity to the vertical asymptote of negative 3 over 2. So watch out for that. Hey guys, don't forget to like and subscribe, but also if you found this video helpful, there's a lot more where that came from. You can click the upper link, which will take you to the whole unit playlist, or you can click the lower link, which will take you to the next video in the playlist. See you there.